Hello, my name is Jacob Kreger, and I'm here to talk to you today about elimination and substitution reactions, specifically the conditions that are conducive to both. At the beginning of this chapter, I found it difficult to discern whether a reaction would be more likely to undergo elimination or substitution, and that's because a lot of the initial conditions for those reactions seem rather similar. If you look, for example, at this singularly substituted alkane, and say it were being reacted with hydroxide, which is both a strong base and a strong nucleophile. In this case, it seems quite possible that you might experience a substitution reaction in which this hydroxide takes over the place of the chlorine. But it's also quite possible that a substituted alkene could occur, and that the hydroxide would pull a hydrogen out, acting as a nucleophile, as well as removing the chlorine. Now, in order to understand which of these reactions is more likely to occur, you must first understand the conditions in which elimination reactions occur, usually with strong bases, with crowded substrates, or in high temperatures. One good way to remember these is that each of these conditions are typically conditions in which you would prefer to avoid. These are conditions that you would prefer to eliminate from your life. I had some friends once who climbed into a pool that had recently been cleaned with bleach, and they were quick to get out of there after they realized that their trunks were becoming gradually white and that their skin was peeling. Crowded substrates, you don't want to be in crowded areas. That just causes anxiety. And in high temperatures, you generally want to go into air conditioning. People generally don't enjoy sweating needlessly. So if you look at this equation again, you'll likely notice that we're working with a very strong nucleophile as well as a very strong base. And this strong base is going to cause this reaction to favor this product. There's also the fact that the single-bonded O to carbon is relatively weak, but at this point in the book, we hadn't learned very much about that yet. So had to go mostly based on the fact that it was a strong base. If you were to increase the temperatures in this reaction, that would simply make even more of this and even less of this. And eventually it would come to a point where this was the only product, particularly if you refluxed the reaction. If we take a quick look at another reaction, say with a tertiary carbon and a halogen attached to it, one thing to note, halides aren't very common in elimination reactions, so don't expect very many halides to come flying in and causing elimination reactions. In this case, let's just work with hydroxide again, since it's an easy, strong nucleophile and strong base. Before the chapter, one might have guessed that a substitution reaction in which the iodine is displaced would be possible, as well as this alkene. But one reason why this reaction is likely to be favored is because this substrate right here is very sterically hindered. These hydrogens are going to push on this iodine, and they're going to make this iodine really just want to leave this compound, simply because it's so crowded. If you increase the temperatures as well, that would also make this even more common. Things only get more complicated when you start mixing in SN1 and E1 reactions, simply because both of them require a weak base to be involved. If we made this into a weaker base, it would be quite likely that you would see a lot of SN1 products, possibly some E1 products as well. E1 usually appears on secondary carbons. It's very, very unlikely to appear on a primary carbon, and it's also quite unlikely to appear on a tertiary carbon. Secondary carbons are the ideal situation. With this particular compound, Since it's a tertiary carbon, E1 would be pretty uncommon, but possible in the presence of a weak base.